Okay, hello everybody. So this is 3.5 video recording 3, and we're going to talk about vertical stretch here. So I'm going to start with the example. Okay, so this is the example. Use graph f of x equals square root of x to obtain the graph of f of x is equal 2 times square root of x. So I want to explain first the vertical stretch. So absolute value of a is greater than 0. A is coefficient. Okay, so let's f of x be original function and g of x equal absolute value of a times f of x is a vertical stretch of f of x by coefficient a only if absolute value of a is greater than 0. So what happened with vertical stretch? We're going to keep the same x coordinate as our original graph. The y value will be multiplied by coefficient of a. So note x values are not affected y values of original values of original function are multiplied by a. Okay, so vertical stretch only when the absolute value of a is positive. Not just positive, it always will be positive absolute value, but greater than 0. Okay, so let's do the example. Let's go back to our example. So we have a function, going back to the example. So example, we have f of x equals square root of x, original, and now we need to graph g of x, which is equal 2 times square root of x. Okay, so here, like you see, we have a equal 2, so our coefficient 2, and like you see, absolute value of 2 is greater than 0, so since that we have a vertical stretch. We have vertical stretch. Okay, so let's graph it. So let's graph f of x equal square root of x, which we graphed that function already. Let's just quickly go back to table value, x, y is equal square root of x, and then we have points x comma y. Okay, so when x is equal 0, y is equal square root of 0 which is 0. So we have a point 0, comma 0. Next, when x equal 1, y is equal square root of 1, which is 1. So we have a point 1, comma 1. And one more point, let's make x equal 4. So then y is equal square root of 4. So we're getting 2. So we have a point 4, comma 2. So that's the original graph. Now we're going to create the table value first for g of x, which is equal to square root of x. And I'm going to use the original graph for that. So again, y is equal to square root of x, and we're creating our 3 points, x, comma, y. So for vertical stretch, there's no change regarding the x coordinates. So I'm keeping them the same. So we pick 0, we pick 1, and we pick 4. We're going to do the same thing. So we have 0, 1, 4. Now, with vertical stretch, what happened? The original y values of your original function, since we already know at least 3 points of original graph, just use them and multiply them by 2, because 2 is our vertical stretch coefficient. So to get the y value, I'm taking 0 and I multiply by 2, so I end up with 0. So to find the y value for our next point, originally we have 1. I'm taking 1 and multiply by 2, so we end up with 2. And the last point, originally the y value was 2. Since we have vertical stretch by 2 units, so use that, take that 2 and multiply by 2, you end up with 4. So again, what happened? We use original y values and we multiply them by 2. Okay, we use the original y value, we multiply by 2. And we use the original y value and we multiply by 2. Okay, so since we have two graphs, let's graph them together. Okay, so again, f of x will be in black, which was square root of x. We had 3 points, 0, comma 0, 1, comma 1, right here. And then we have 1, 2, 3, 4, comma 2, right here. So let me create it. So this is f of x. Okay, now g of x equal to square roots of x. So we have a point 0, comma 0. Then we have point 1, comma 2. And then we have point 4, comma 4. 3, 4, 4, comma 4, which will be here. So like you see with vertical stretch, what happened, the graph is getting closer to the y value. So this is vertical stretch. So again, let's write a note. Vertical stretch. Okay, the graph is getting closer to y-axis. Okay, next what we're going to do, we're going to talk about vertical compression. Okay. vertical compression. Vertical compression. So what's going to happen? Our graph will be, original graph will be compressed, which will be more flat, and it's going to actually start getting closer to the x-axis. So let's just quickly describe that. Let's f of x be original function, and g of x equal a times f of x is vertical compression only if absolute value of a is greater than 0 and absolute value of a it's less than 1. So a is a coefficient. A is a coefficient okay, and for example, for vertical compression, example of vertical compression is y equal 1/2 x squared. Okay, so this is the example of vertical compression because our coefficient is a. In this case, a is equal 1/2, and like you see, the absolute value of 1/2 it's definitely less than 1. So when your coefficient, absolute value of coefficient is smaller than 1, then we're going to have a vertical compression. Okay, parent function, original graph, of course, it's y equal x squared. So let's do the example with the vertical compression. So example, use the graph f of x equal absolute value of x to obtain g of x, which is equal 1/2 times absolute value of x. So like you guys see, because of that 1/2, we have vertical compression. We have vertical compression. Okay, so with the vertical compression, the new graph, just write a note. The new function g of x will stay farther away from y-axis. Okay, so farther away from y-axis, that means it's going to start getting closer to the x-axis. Okay, so quickly, solution of this. Okay, so original graph f of x equal absolute value of x. We graphed that already. This is the original. So let's use 3 major points to graph the absolute value function. So let's just quickly use them. We'll graph that in a couple examples. So you have a point 0, 0, you have a point 1, 1, 2, 2. Okay. Now let's graph g of x, which is 1/2 times absolute value of x. So this is how the points will behave. So no changes regarding x's. So I'm using the same x coordinate equals 0. So we're having x still equals 0. However, original y coordinate will be multiplied by 1/2. So we're going to have 0, because 0 times 1/2 is 0. Then the next point, we're going to still use 1, because we're using the same x coordinate, so it's 1. And the new y value, you're going to use the old y value, which is 1, and multiply by 1/2, so we're getting 1/2. And the third point, we're going to use exactly the same x coordinate, which is 2, because we only have vertical stretch, nothing about horizontal change. And to get the y value, use original y value, which is 2, and multiply by 1/2, so you're getting 1. Okay, so now we're going to graph both of them together. Y, x. So on my unit, I'm going by 1. So again, in black, it's going to be f of x. So we're having point 0, 0. Then I have 1, 1. And then I have 2, 2. 2, 2. Okay. Okay, and of course you can, we already know how absolute value graph looks like. So if you have 1, 1, you also will have a point -1, 1, because absolute value graph is symmetric with respect to the y axis, and that point 2, 2 right here will be, we also have -2, 2. So again, that's the absolute value. Okay, so this is f of x equal absolute value of x. Now we're going to graph g of x. So we have a point 0, 0, 1, 1/2, and then 2, 1. So that way. And on the other side, you have -1, 1/2. And you will have -2, 1. Okay. And again, this is just sketch, but I want to just show you that the graph g of x, which is equal 1/2 absolute value of x, because of the vertical compression, the graph is staying far away from the y-axis and start getting closer to the x-axis. Okay, so that was vertical stretch. Next, we're going to talk about horizontal stretch and horizontal compression. So everything what you hear about horizontal, so it's opposite of what you see. So we talk about it with pushing graph horizontally to the left and to the right. Now we're going to talk about horizontal stretch and compression. Okay. So let's talk about, let's start with horizontal stretch. Horizontal stretch. Okay, so horizontal stretch. So let's f of x B original graph then g of x equal f b times x is horizontal stretch only if absolute value of b it's a coefficient, of course it's greater than 0 but less than 1, and in red, and if absolute value of b it's greater than 0 let's put it that way, sorry, and if absolute value of b it's greater than 1, we have horizontal compression. So we have to get used to have it. Everything what affects x-axis horizontal, it's opposite of what you see. So just quickly give you the example. Let's f of x equal let's put it that way. I'm gonna give you a nice example. Let's f of x it's equal okay. Hold on. I think it would be easier. Okay, that way. Hold on. I think we have a nice example. I can just go back to PowerPoint. Okay, so just hold on for seconds. And that's one. Okay, so let me go back to that PowerPoint. This is still section 3.5. Where is that PowerPoint? Right here. So we can see it better. Okay, and the last slides have the horizontal graph function using compression and stretch. Okay, so we did this one, and right here, okay, okay, horizontal compression, horizontal stretch. Okay, so how does this look like? So here what you guys see, you see the function of sine. This is the trigonometric function, but this is the original graph. So you see a couple points. So I want to explain it, how the graph will behave when we're dealing with horizontal stretch or compression. So this figure right here shows you that when you take your original graph and you have just coefficient in front of entire function, so what happened here, we're dealing with vertical stretch by 2 units. So you take your original points, so you're keeping the same x coordinate, and the original y value, like you see, were multiplied by 2. So originally you had point pi over 2 comma 1. Now we end up with a point pi over 2 comma 2. So the graph stretch vertically. Now when we have horizontal stretch, horizontal compression, okay, so what's going to happen? The graph either will stretch horizontally or compress. So using that example, like you see, inside of the parenthesis, you have 3 times x. So what that means, we're going to have a change with respect to the x coordinates. And based on the definition, okay, because our coefficient is 3, absolute value of 3 is definitely greater than 1. Since we have coefficient, which absolute value is greater than 1, we're going to have a compress. So it's opposite of what we see. The graph will compress horizontally. So look what happened, okay? We compress that graph comparing to original. Okay, so we're using exactly the same y coordinates. I'm going back to original graph. You had pi over 2 comma 1, and I'm using points 5 pi over 2 comma 1. Look what happened here. We still have 1 and 1, the same y coordinates, but x coordinates were affected. So how they got that pi over 6? So they did, since we have compressed, they took original x coordinate and they divide by 3, okay, because we compress. So again, x has to shrink, okay, that's what happened. So let me just write this down. Okay, so example, just going back to that PowerPoint example. And again, when we deal with horizontal compressed stretch, that's usually actually, you see that a lot with trigonometric function. So f of x equals sine of x. So I'm going to example of PowerPoint, and then g of x equal sine of 3x. So like you see, x, it was affected. So because here, going back again, I'm using the sine function because that's what you guys had on the PowerPoint. Because absolute value of 3 is greater than 1, we have horizontal, okay, compress, not stretch. Again, it's opposite. You see bigger coefficient, x being multiplied by bigger number, that means it's going to be compressed. So just quickly to give you the idea, because after this class, actually, you're ready to take trig. So y equals sine of x, okay, original graph. Okay, they use the points, couple points. I'm just going to explain that based on the pi over 2, 1, and 5 pi over 2, comma 1. So that's the original points, x, y, and because we have horizontal compression, okay, because we have that horizontal compression, g of x, which is equals sine of 3x, is horizontal compression. So what happened? The y value will stay the same. So originally we have 1, we're still going to have 1. What's going to happen to x coordinate? So you're going to take the original one, which was pi over 2. Since we have compressed, you need to divide it by 3. So pi over 2 divided by 3 is the same as pi over 2 times 1/3, which will give you pi over 6. So that's how you saw on the PowerPoint that the x-coordinate of horizontal compress was pi over 6. So it's getting closer. And the second point, I'm going to use exactly the same y-coordinate. With horizontal stretch compress, there is no change regarding y-coordinates. And to get the new x-coordinate, you take the original one, which was 5 pi over 2. Because we have compressed, so divide by 3. Why are we dividing by 3? Going back to our original function, we have sine of 3 times x. So technically, to get our x, we need to divide by 3. Divide by 3. So you're getting 5 pi over 2 times 1/3, which is 5 pi over 6. Pi over 6. Okay, so for horizontal compress, to get the new x-coordinate, take original and divide by the coefficient which you see in front of new function. Okay, note for you guys, for horizontal stretch, g of x will look that way. You're going to have sine 1/3 times x. So that's going to be horizontal stretch. So pay attention, in front of x you have a number which is less than 1. So this is horizontal stretch because absolute value of 1/3 is less than 1. Okay, so again, what's going to happen? I'm just quickly going to explain. So f of x, not this color, f of x equals sine of x, and I'm going to use the two original points which we use, pi over 2 comma 1 and 5 pi over 2 comma 1 for g of x, which is the horizontal stretch, which is sine times 1/3 times x. So to get the new points, okay, what's going to happen, you take original x, which is pi over 2, and we have a stretch, so now you need to multiply that by 3. Multiply that by 3. Because the coefficient right here was 1/3. So again, why multiply by 3? Because my idea is I want to get here original function, which is sine of x. So what I need to do to that coefficient to get x by itself, I need to multiply by 3. So we multiply by 3, and we're getting 3 pi over 2. 3 pi over 2. So 3 pi over 2 will be the new x-coordinate, y-coordinate will stay the same. And the same thing with the second point. Originally you have 5 pi over 2. Okay. Now, because of horizontal stretch, your coefficient in front of x is 1/3. Again, the idea is that you're trying to go back to original graph. So to get sine of x, I need to multiply that 1/3 of x times 3 so I can get x by itself. We have horizontal stretch also, so that means x has to stretch, so we're going to multiply that by 3. And we're getting here 15 pi over 2. And there's no change regarding y value. I'm going to skip graphing. the horizontal stretch. And next, what I want to talk about it, I want to go back to PowerPoint. Where's that PowerPoint? I want to go back to this PowerPoint. The last part of section 3.5 talks about using reflection about the x-axis and y-axis. We talk about it, so I quickly want to talk about the PowerPoint. Reflection about the x-axis. What's going to happen? You're going to have a minus in front of entire function. So graph the function f of x is equal to negative x squared, find the domain and range. So what happened here, on this solution, you see x and y, they pick some points for a function y is equal to x squared. So you have point negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, and 4. Because you see the minus in front of entire function, that means your graph is going to be reflect over x-axis. So y values, like you see in the middle, stays exactly the same. And because you flip over this graph with respect to the x-axis, the original x-coordinate will change to the opposite. The original y values will change to opposite. So like you see, 4 will become negative 4, 1 will become negative 1, and so on. So the best way to see reflection about the x-axis, like you see in black, you see original function, and we just flip over with respect to the x-axis. So x value stays the same, y values of original graph change it to opposite. Okay, so here you have a definition of reflection about the x-axis. So f of x is original function, and that original function, if it's multiplied by negative 1, then the graph of new function, which is negative 1 times f of x, is the reflection about the x-axis. Okay, so it's negative 1 times original function. And next one, it gives you the reflection about the y-axis. Okay, let's go back to this one. So let me just write this down for you. Reflection with respect to x-axis. So f of x is original graph, and if you have reflection with respect to the x-axis, g of x will be equal negative 1 times original function. So I'm putting that parenthesis. So you're going to see that negative coefficient in front of entire function, okay? So g of x is reflection with respect to x-axis. So how that's going to look like, going back to the example, let's say if your points, let's talk about example, your original graph f of x, okay, I'm not giving you function, but let's say it has a point 1, 2, 3, 5, okay, so g of x, which is the graph negative 1 times original function, okay, we have reflection with respect to the x-axis, so the new points, what's happening here, x coordinates stay the same, the y values will change to opposite. So the second point, x will stay the same, the y value will change to opposite. Okay, that's what's going to happen. And let's give you the definition, reflection. About the y-axis, okay, so definition will be here, f of x is original graph, so g of x, it's equal f of negative x. So what happened here, this graph is reflection about y-axis. So what happened here, not the entire function, but -1, it's going to be your original x, it's going to be multiplied by -1. Okay, so only x is multiplied by -1. Okay, so example, f of x original graph and the g of x equal f of negative x, okay, is a transformation, okay. Of f of x. Okay, technically what we're doing, flip over y-axis, so I'm going to use the same points like before, 1, 2, 3, 5. So f of x has points 1, 2, 3, 5. So g of x, we're flipping over the y-axis, which means y will stay the same and x will change to opposite. Okay, so that's how it works. Okay, and one more example and we done. Hopefully this video is a little long. Hopefully I will be able to save entire video and I won't have to cut it. So example, combining graphing procedures. Graph the function f of x equal 2 over x plus 2 minus 1. Find the domain and range. I will skip the domain and range. I just want to talk about the transformation. Okay, so how are we going to do it? Solution. So first, find original function. So don't forget that this is the transformation right here. Okay, so we're trying to figure out what was the original graph which we used to create this one. So original function will be y it's equal 1 over x. Okay, so that will be original graph. Okay, step 2, second. Okay, so what we're going to do. So look what happened. Now we're building our new function. So to get 2 over x, again, I'm working only with this part right here. What we have is what type of transformation we have. We took original graph to do that. So this is the same as 2 times original graph, which is 1 over x. So let's describe that transformation. Here we have vertical stretch by factor 2. So I want you to recognize the transformation by factor 2. Okay, so, okay, that's second. So we're building the new function. Let's talk about third. Okay, what's going to happen? Now we're going to work with y, it's equal 2 over x plus 2. Okay, so 2 over x plus 2 right here. So look what happened. Now, again, we're going back to the second step right here. We have a function 2 times 1 over x. Now look what happened. X is affected, we're adding 2. So since we adding 2, so we have that horizontal shift. You see plus, that means you moving graph 2 units to the left. So here we have that 2 plus 2, we have horizontal shift of this function right here. From step 2, horizontal shift by 2 units to the left. Okay. Okay, and next, step 4, we're building the entire graph, which is y it's equal 2 over x plus 2 minus 1. So this is the last part. We have that negative 1, which is standing by itself. That means the graph y equal 2 over x plus 2 has to be pushed down 1 unit. So that 2 right here, I'm sorry, that negative 1, that's going to be our vertical shift. We're pushing graph 1 unit down. Vertical shift. Down 1 unit. Okay, so we have it. And again, to graph that, I will just go back to PowerPoint because they already graph it. What is important for me that you actually can do those steps. You can just build the given function starting from original function and explain all the transformation. So here, talking about the step 1, you see here y is equal 1 over x, reciprocal function. Then we build the graph y is equal 2 over x. So we talk that we have that vertical stretch by 2 units. So we use the first graph and our y coordinates of the 3 given points were multiplied by 2. Okay. Next, I'm talking about step 3. To get into step 3, you have y is equal 2 divided by x plus 2. So you see that x plus 2, that means your graph, the second graph, has to be pushed 2 units to the left. So y coordinates won't change. The x coordinates of graph 2 will shift 2 units to the left. Okay, so like you see, the graph 3, we push, we use the second graph to show that horizontal shift 2 units to the left, which is right here, graph C. And the last one was our horizontal shift 1 unit down. So you're going to use graph C and you're going to push it 1 unit down. So you're going to push each point of the graph 1 unit down. And this is what we end up with. This is final graph. Okay, so I'm going to stop here. We also have one extra example, which you can study at home. So that's it of section 3.5. Please send me emails with any questions. Thank you.